Hey, thanks for joining. I'll be giving a quick little demonstration of this tool that I wrote in Excel VBA, which is handy for simulating some cyclic behavior. This particular program is written in Excel VBA. It uses a bilinear kinematic hardening model, utilizing the backstress to kind of keep track of the yield surface throughout space. If that means nothing to you, that's fine. I'll explain some of those things as we go along, and hopefully it'll make a little bit more sense. So why don't we jump right in. So if I run this guy here, you can see this would be a typical kind of monotonic loading. I think everyone would expect this behavior, so nothing new here. The bilinear hardening really just means that, so for the first section here, this is Young's modulus up to the yield point. Past that, you'll have a linear hardening model, so this goes up to about 70 KSI at 20% strain. This is engineering stress strain, by the way, and so again, nothing new or surprising here. So why don't we run it to 35 KSI and then release the load, and let's see what happens. So I think everyone should understand and would expect this behavior. So we load it up, hit the yield point, and we're increasing the load to 35, accumulating plastic strain, and then we release it down to 0, so we're following the slope back down. And this would be the kind of plastic strain that was accumulated throughout the cycle. So again, nothing new here. I think most people would totally expect that. Let's just do another quick, straightforward example, and then we'll jump into some of the more interesting things. So if we were to run this back and forth below the yield point, everyone would expect that this is all in the elastic range. We didn't hit the yield point, so we're not getting any straining. So again, should be nothing new. So why don't we try putting this to let's say 40 KSI, and I think if we were to load this in compression, our yield is 30, so we would expect this thing to yield at 30 KSI, so in compression. So why don't we run that to, let's say, negative 35, and let's see what happens. I'm just going to increase a little bit more. Okay, so what happened here? We would have expected this thing to yield at 30, and it looks like it yielded at 20. So this is a result of the kinematic hardening model, which essentially assumes that there's a translation in the yield surface. So let me just talk about that really quickly here. So if you were to imagine the yield surface, if you're probably familiar with kind of the typical von Mises kind of ellipse that you would plot. So this would be your yield surface, and when you start hardening or strain hardening, I should say, there's different models that can be used to describe that behavior. One of them is isotropic hardening, and that's essentially where the yield surface just grows in all directions. So this should be uniform. So this would be considered isotropic hardening. And And this works for monotonic loading, meaning loads that aren't reversed and cycled. So this will not capture the behavior that we just saw. So what is kinematic hardening? So kinematic hardening basically assumes that the yield surface basically translates in space as you're loading it. So if we strained it in this particular direction, our yield point has increased in that direction. But you'll also notice that on the compressive side, it also shifted, and that is why on the compressive side it's actually smaller, which is exactly what we see here. So we hit 30 kSi and we basically did a shift of 10 kSi delta, and you'll notice that we're exactly 10 kSi yielding earlier than our initial thing. So this phenomenon is called the bauschinger effect, and the kinematic model lets you kind of predict that behavior. You'll notice that because of the translation of the yield surface and there's no growth in it, your yield surface will always have a constant kind of length to it, which is equal to twice the original yield. So you can see here it's between 40 and negative 20, so a delta of 60 kSi, which is exactly 2 times the yield strength. So that will remain basically throughout all the cycles, and that's just part of the kinematic model. So why don't we go ahead and take a look at what ratcheting is, and I'm just going to paste a cyclic step here, which basically has 8 kSi mean stress, and we're going to basically do displacement controlled alternating about 0.3% plastic strain on that mean stress. And I'm just going to decrease this to just 1 increment so it kind of goes a little bit faster. So let's let that run and take a look at what happens here. So you can see with every single cycle the strain is accumulating and this thing's shifting over to the right constantly. So that's essentially what happens when you're ratcheting. And one thing to observe is that it's moving in the kind of direction of the mean stress. So you can imagine the mean stress here is at 8 kSi, and as this thing is moving, you can see with the hardening slope, it's shifting, and it might be hard to tell, but you can tell each increment is getting smaller and smaller versus, let's say on the front here, the amount of strain you're accumulating per cycle versus there. So you can see that it's actually starting to slow down and somewhat stabilize. And it's going to become stable when this thing has shifted over enough so that this curve is centered on that mean stress. So that's kind of one of the driving mechanisms, is you need to have that kind of mean stress for the ratcheting to take place. So this one, it ran, I forget how many cycles I had it, but obviously it didn't fully stabilize, but you can definitely tell it slowed down. So I'm just going to increase the hardening right here and rerun that. The 200,000, that's kind of like an average strain hardening from yield to ultimate, but it's definitely in the kind of smaller strain ranges you can have a higher slope. So let's see what happens if we run this. So same as last time, it's still ratcheting, and I would expect that this one is hopefully going to start approaching stabilization much earlier. You can kind of see that the peak, it's almost at 8 KSI, higher than what it originated at the 30. You can kind of see here that it's already starting to slow down, and you're going to see that effect here more and more. Yeah, look right there. So it's just barely crawling. You can tell the density of the lines that it's kind of painting for us. So it's definitely kind of stabilizing right in that spot. And if I let it run a little bit more, it would have eventually just stopped completely and basically just ran in a continuous loop there. So that was a quick kind of demonstration of ratcheting behavior, which slows down eventually and would come to a complete stop and stabilize. And I guess just for interest's sake, maybe I'll run one more. And why don't we run the initial cycle so that it goes to, let's just say 0.017 right off the get-go. And we'll see if that kind of speeds up the stabilization. So if you had an initial loading that had significant strain in that direction of the mean stress. So you can see we kind of jumped right over to here, and you can see that each increment is already much smaller because we kind of went right into that spot where the mean stress is really close to the kind of the average of the loop. And yeah, so right now it's pretty much stable. It's not really moving anymore at this point. So it's just kind of cycling back and forth, maybe a little bit. But yeah, for the most part, pretty much stable. So you can kind of see the effect that your loading history has on it. So it's possible that if you had an initial kind of higher loading, you can stabilize earlier. Looks like it was still going a little bit at the end, but definitely nothing like what it was the first time we ran it. So that's just a quick little demonstration showing the little tool. Happy to run other cases if people are interested or have questions and wanted to chat about it. More than willing to take the time to explain it. If people are interested in doing something similar or coding it themselves, it's not too bad. So thanks again for listening, and yeah, feel free to reach out. Okay, take care.